We're going to be talking about end behavior of polynomial functions, and what you need to know is that you're going to be using the leading term each time that you want to describe end behavior. So if we're looking at these examples down here, all I would be using for my end behavior would be that leading term, which has the highest degree. So when we get down to that point, we'll be using just those leading terms. Okay, polynomial functions are going to have a leading term, and that term is either going to have an even degree or an odd degree, and it will either have a positive leading coefficient or a negative leading coefficient. So what I'm going to do is I'm going to relate these even and odd degrees back to a couple of parent functions that we had. So our parent function that had an even degree would be like y equals x squared. Our parent function that had an odd degree is like y equals x cubed. And remember that our y equals x squared was a parabola. Our y equals x cubed was that squiggle graph. So I want to look at the positive and negative leading coefficients. So for example, if I had y equals 2x squared, that would be a parabola with a vertical stretch of 2. So my graph would start at 0, 0, and then it would go over 1 up 2, over 2 up 8, over 3 up 18. And so my graph would appear like that. If I had y equals negative 2x squared, for example, then this is a reflection across the x-axis with that same vertical stretch, and that graph would look like this. So one thing that we should notice about even degrees is that both ends go in the same direction. And we're going to use some mathematical lingo to describe the end behavior. So when I ask you about the end behavior of graphs, this is what I'm asking you for. I'm going to ask you to write as x approaches negative infinity, f of x approaches, and we'll fill in this blank again in a second, and as x approaches positive infinity, f of x approaches, and we'll fill in this blank. So each time you have end behavior, you're going to be starting out the exact same way. As x goes to negative infinity, f of x goes somewhere, and as x goes to positive infinity, f of x goes somewhere. So each of these will be the same, so I'm going to go ahead and fill in all of these boxes, and then we'll talk about what I mean by these expressions. Okay, each time that I write as x goes to negative infinity, what I mean by that is the left end of the graph. And then each time I write as x goes to positive infinity, what I mean by that is the right end of the graph. So on the first statement, as x goes to negative infinity, I want to look at the left-hand arrow of my graph. On this one, it's y equals 2x squared. The left end of my graph is going up. So to write the left end of my graph goes up, I'm going to write f of x goes to positive infinity. Now if you look at the right end of the graph also goes up, so that's going to be positive infinity as well. If I look at my second example here, y equals negative 2x squared, where I have an even degree, negative leading coefficient, this means the left end of my graph, the left arrow is going down. So f of x goes to negative infinity. So that's what I need to write if that end is going down. As x goes to positive infinity, the right end of my graph is also going down, so that will be negative infinity as well. Let's go ahead and look at our odd degree. An odd degree graph would be like y equals 2x cubed. 2x cubed, well, our x cubed graph was started at 0, 0, and it went over 1, up 1, over 2, up 8, over 1, left 1, down 1, left 2, down 8. So this graph is a squiggle graph like that. And if I had y equals negative 2x cubed, that's going to reflect the graph over the x-axis. So it just flips it upside down like that. So to fill in our end behavior, we would write as x goes to negative infinity, that means the left end of my arrow is going down, so that will be negative infinity. As x goes to positive infinity, that's my right end. The right end is going up, so that will be positive infinity. As x goes to negative infinity, the left end goes down. As x goes to positive infinity, the left end goes up. Left end goes up. The right end goes down, negative infinity. So on an odd degree, the ends go in opposite directions. And you may notice that in order to determine if you have a positive or negative leading coefficient, you can just really look at the right-hand end. If the right-hand end is going up, it's a positive leading coefficient. If the right-hand end is going down, it was a negative leading coefficient. So you might use that to your advantage later on. So let's look at our examples that are written out here, just in terms of end behavior, which is what I mean by direction. So on my first example, negative 6x to the 5th. The degree of that term is odd, and the leading coefficient is negative 6, so it is odd and negative. Now I know that in an odd function, the ends go in opposite directions. If it has a negative leading coefficient, my right-hand end is going down. So I already know that as x goes to positive infinity, f of x goes to negative infinity. And since it's odd, they need to go opposite directions. So as x goes to negative infinity, that's the left end, f of x is going to go to positive infinity. We'll come back and talk about y-intercepts and number of roots and number of turns here in a second. My second example is x to the 4th, which is an even degree. And the leading coefficient is positive 13, so it's even and positive. Even means both ends go the same direction. Positive means my right end is going up, so I know that both of my ends are going up. So when I fill in, remember that this part is always the same. As x goes to negative infinity, f of x goes to. As x goes to positive infinity, f of x goes to. This just means my left end, since it's going up, I'll have positive infinity. My right end, since it's going up, is also positive infinity. Third one, degree is 16, which is even. Leading coefficient is negative 427, so even and negative. Even means they both go in the same direction. Negative means my right end is pointing down. So I can fill in all of this information first, and then I can say, okay, negative leading coefficient means the right end, which is the second statement, points down. Even means they go the same way, so both of them are negative. And then this last one, the degree is 7, which is odd. Leading coefficient is 32, which is positive. So if we fill out as x goes to negative infinity, f of x goes to. As x goes to positive infinity, f of x goes to. So positive means the right end is going up, and odd means they go opposite directions, so the left end will be negative infinity. Y-intercepts. Our information here says y-intercept is where the graph crosses the y-axis, and we find that by substituting 0 in for x, then solving, and we write it as a point, 0, comma, number. So on my first one, if I put 0 in for x, 0 in for x, that just leaves y equals 12. So my y-intercept will be 0, 12. Second example, put 0, 0, 0 in there. That gives me y equals -9. So 0, -9. Put 0 in for x, I get 8,493. So 0, comma, 8,493. And finally, put 0 for x here, I get y equals +1. So 0, 1. The number of roots that a polynomial function will have, and it's actually the number of complex roots, because they might be real roots and they might be complex roots. But the number of complex roots total will be equal to the degree of the polynomial function. So as we work down our row, the degree is 5, so it will have 5 roots. The degree is 4, it will have 4 roots. This degree is 16, it will have 16 roots. This degree is 7, it will have 7 roots. And the number of terms that a polynomial function will have is going to be 1 less than the degree. So number of terms, and it doesn't have to have that number of terms, but it will be at most